Okay, so good morning and welcome to this 13th session of Memory Design and Test course for this semester. And as I said before we start, let us just have a quick dip check and quick feedback on how the class is going for you, any specific inputs that you want me to take care of, anything that you need to change or, so please, because in the feedback that I received from Opine, there's not much except, as I mentioned, a little more of review about what we did in the last class. Most of the students feel that the pace of the class is fine, but always there will be a few who will feel that it's running a little fast. But for those of us who are here, I just want to have a dip check as to how do you feel. Any feedback for the class, anything that you think should be changed, improved?
So when the feedback form was floated, till then the pace was fine. Like I'm talking about myself. And from the last two lectures, from the last two lectures, it was fine also. But in between those lectures, those were quite a bit fast for me.
Okay. What about others?
Sir, small thing, I realized that since I could not attend many office hours and uh, due to other commitments, so if is there an option that we can get an assignment to cover up for some points?
So we have the review quiz, na? Which is released
Yes, sir,
every week.
yeah, that's also that one like and the 10% and many components. Can we have some assignments?
No. See, the thing is, the guideline is that we should not have more than 5 components which are evaluated. So the quizzes, as you also know, even they are self-graded quizzes. There's nothing that we add into it, and they are not being directly used for your scores also. So that is where I'm not really intent on adding many more assignments. In fact, my courses do not usually have assignments. We have projects. So projects hain aapke paas, you just start working on the projects. That will bring in the required learning. What kind of assignments are you looking for, Deepank?
To equip us with basic testing strategies for, like, suppose because we are not working on every project, so basics like uh, how to test the bit shell for suppose SNM or things like that.
Okay, but we will see. A few of the project teams have memory cell design as a part of their project, but there are many who do not have that. So we will see in the project presentation that you guys have to make on the day of the exam. We will see that the details are provided there.
Okay.
Okay. So what date is our exam? Mid-semester exam?
11th.
11th.
Next Friday.
So
Okay. So then we will have the presentation in the morning part, 10 to 1, and that is when we will see that all the groups are presenting in detail about their plan to validate and do something. Okay.
sir, project presentations will be on 11th itself.
Yes. 11th morning before the exam.
So can you do after that? I mean, we have exams and we'll be reviewing.
So
Actually,
that is the
for
challenge. See, that is the challenge because other days you will have other exams.
No, sir. Actually, like last exam is on Sunday itself of this MTech group. I think it's BDF. After that,
No,
but
we do not have only MTech students in this class, Raghav.
Oh,
We have
right.
BTech students also.
Yes, sir.
So that is where the challenge is. Otherwise, I will have to take this presentation and during the mid-semester break, which I do not want to take. Otherwise, you will again cry foul that mid-semester break ke dauran kuch ho raha hai. So 11th is the day when the evaluation of the course is anyway planned. We will just do it in the morning.
So I don't think that most people will have any issues with the mids and break. I mean, they would be okay with that instead,
Yes, sir,
because
can
I
I
could
might
see.
have an issue, na, Raghav?
Yeah, yes. So actually, I could see that people were having the day before they were having some ALD exams also all day long. So they were originally I were requesting Sumit sir also to plan out this also.
Yes, so
Maybe.
that's what I wanted to say. We have full day exam of AELD just a day before, like on 10th.
Hmm.
So it will be quite a bit difficult for us.
Yes, sir.
You know it well in advance now. You can prepare this presentation right away.
Sir, preparing for presentation, again, managing for the theory exam, so it will be very much constrained, sir. So it will be very difficult to manage things, sir. Everything piling up one after the other.
Okay, we will do a quick check in the classroom. If there are people who are willing to conduct these presentations in the mid-semester break, I'm fine with it. Even if one person says no mid-semester break, we will not do it in the mid-semester break. We will do it on 11th then. Okay.
Sir, it will be very difficult for us, sir, because
Fine. We need to plan things. There is time. Right? Come to think of it like this. You are working in some organization. Kitna? Most of you are will be joining some organization within 1 year of now. Some industry will be joining within 1 year of now as an intern or as an employee, something like that. Am I right? So, do you think you will be able to talk to the customer and say, no, please, मेरे घर में कुछ है या मेरा ये है या मेरा वो है, and therefore I will not be able to deliver the product on this date? ऐसा होता है? So again, we will see if we can do it on 15th or 16th, something like that, just at the beginning of the mid-semester break. But I'm not sure. Okay, because there may be students who have exams on 15th also. Exams are on till 15th, na? The exam schedule is on till 15th. Am I right?
yes, sir.
Yeah. So there could be students who have exams on 15th also. So then it spills over to 16th. And we have, so as I mentioned, it is not convenient for me on those days because we have an audit which we have to prepare for and which we have to be present and conducting the audit. And there is a NAC audit that is going to be on campus on that day. So we will see if we can manage something. Okay. Other feedback. We'll come to this. Don't worry. Other feedback. So Deepank, so I realize you mentioned that you would want to have assignments which would help you create these small setups for S&M or right margin analysis and so on. Am I right? Did I understand it correctly?
Yes, sir. Instead of quiz, like once we can have such, like for 1 week we do not have quiz. Replace not like, I don't know. This is session.
See, the quiz has its own role. The importance of quiz is that you kind of review what was done in the class. Okay. And they are not interchangeable.
Okay,
What you're
sir.
asking is, you are asking for more EDA experience. I believe in this course, you will have sufficient EDA experience in your projects anyways. You want some more, you can always try it out yourself, is it not?
Yes, sir.
All of us, in our office hours, we are more than happy to support you with any questions that you have, even beyond the class, is it not? If you would come to Bilal or come to Amir or come to Gagandeep and ask ki, or even to me and ask ki, I did this kind of an S&M analysis, is this correct? Will anyone say, no, this is not what was expected. We will not answer your question. Will anyone say like that?
No, sir.
So if you're willing, you do it.
Okay, sure, sir.
Because
Sure, sir.
as soon as I assign it for the class, then for many of you, it may become a burden. See, Deepank, you are interested in learning this, you can do it. Others who are just doing it as another course, they will see it as a burden. Oh, one more assignment. You see that?
Yes. Okay, sir. I did not think it. That's true. Okay.
Yeah. Okay. Anything else? Okay, great. So then what were we discussing in the last class? What were we doing in the last class?
So we looked at statistics of VLSI, the the mean, the the mean, the spread, and the replica path, the replica bit line path.
Mm-hmm. So what kind of distributions did we talk about when we were discussing the statistics in VLSI?
Basically, we talk about the normal distribution, but there
Mhm.
can exist there exist different distributions like Rayleigh or the Poisson's distribution when the samples go very high.
Okay. So where did we talk about, you remember we talked about log normal distribution also? What kind
Yes,
of output variables will follow a log normal distribution? I mentioned that.
I mean, in which case we consider for log normal distribution? Is that your question, sir?
Yes.
For leakage, sir. For
Leakage.
leakage.
Yeah, because leakage is dependent on exponential of VT, and VT is normal. So leakage kind of becomes log normal. Okay. What do you understand by process capability? There were two variables we looked at, CP and CPK. What do they represent?
Sir, CP represents how better we are able to fit fit the design between the upper and the lower limits of the specification, whereas CPK is a measure which decides whether this particular process can be repeatable or not.
Mm-hmm. Okay.
CPK was the process capability, I think. CPK one, sir.
Both CP and CPK comment about the process capabilities.
Yeah, both are about process capability. So one is about the spread, the local spread that you will have on any lot. And the other is about the capability to achieve the target specification. In terms of you wanted design to be typical, so how capable are you to reproduce the typical lot over and over and over again? If the target was slow, so why would you want to target a slow lot?
So if we have the margins for the variations, then we might want to target the slow lot as well.
The leakage, to lower the leakage.
Low leakage. Yeah, so for example, there could be an application that does not require very high performance and it is very sensitive to leakage. For such applications, you may want to target the slow lot. When would you want to target the fast lot? Would you ever want to target a fast lot?
Yes, sir. Fast lot because the performance as well as the power, dynamic power.
Okay, what do you mean by dynamic power?
Because if the speed with which the circuit is operating is very high, then there can be the larger dynamic power which can come into picture.
Mm-hmm.
So then the fast lot can provide worst results with respect to the power.
So as a product engineer, do you want to target fast lot? Because it can fail.
So it depends on the trade-off, right? And it's trade-off between speed and the power which we have.
Mm-hmm.
So I mean, if the customer is okay with the power loss and he wants more speed, then that's fine. I'm like not test it on a fast lot.
So see, typically fast lots would have much higher leakage. They can also run faster. So what is done is, if there is an application which you understand will always be on, So there is an application where 90% of the chip is continuously active. Then you would say that, okay, I want high performance, and this device will the most of the transistors over here are going to be active throughout. So I will want to go for the fast slot, and instead of operating at 1.1 volts, I will operate it at 1.05 volts, or I will operate it at 1.0 volts. So what happens? You get the same performance as earlier, but now by operating at 1.0 volts, you reduce the dynamic power. The leakage is higher, yes, for sure, but the recovery of dynamic power is much more significant because you realize that most of your circuit is always active. Are you able to see this? Any questions around this? Okay, so with that, then we start our today's journey on.
Sir, actually, the last point I couldn't get it. So, if we are activities more, then how is the dynamic power recovery is more?
Because we reduce the voltage of operation. Na? We said it can operate at 1 gigahertz, even at 1.0 volts. I don't need to keep the voltage at 1.1.
Okay, so we are in the equation we are reducing, we are increasing activity, but B is reducing. But B
Activity
square.
will remain same. See,
Yeah,
if you
okay.
have to run one program, the activity will not change. Activity was what it was.
Yeah, right. So,
And you'll also maintain the same frequency. But because you were on the fast slot, you could now operate at a lower voltage.
so, but will be considering the leakage part here also. I mean, that will.
Yeah, so that is why I said these are for the applications where you know that leakage is not that big a constraint because most of the devices are always on. They're continuously active.
That leakage is there.
So because the devices are active, they will anyways toggle, and the leakage will not bother you too much. See, in typical SOCs, digital SOCs, most of the time the devices are sleeping. You're not activating everything all the time. But there are applications, for example, network routers, where it's continuously on 24 hours, full throttle. So then you want high performance, but you do not want you're not really as much bothered about leakage. Leakage continues to be a small component of the total power consumption.
Yes, sir.
Okay, so today we will talk about then what is called as, just give me a second. I entered into the presentation mode at the wrong slide. We will talk about yield recovery. Okay. So what do you mean by yield recovery?
So the chips that are out of the range, we are trying to make them in range in the USL and LSL, which are out of bound of USL and LSL. So by increasing 6 sigma, for suppose if we are taking 6 sigma, then increase it to more than 6 sigma.
So
or make some variation such that our graph fits into this USL and LSL.
So which graph, Vaishnav?
Gaussian graph.
Okay. So see, yield recovery, when we talk about yield and its recovery, we are actually talking about when silicon is already available. So now you're not talking about fitting something in the USL and LSL. You already have your distributions there. And okay, electrical yield recovery can typically be done by modulating the voltage. If there are set time failures, you could operate the circuit at a lower frequency, or you could operate at a slightly higher voltage. If there are hold time failures, you want to lower the voltage, increase the delays here and there, and so on. So hold time failures are typically non-recoverable on silicon, but higher setup time failures can still be recovered by modulating the clock frequency. That is one aspect of yield recovery, electrical yield recovery. But today what we are going to talk about is physical defects and yield recovery from physical defects. So what do you mean by physical defects? So remember this. What is this? Hello? What is this?
Layout of a 60S RAM cell, sir.
Layout of the 60S RAM cell. So now when I'm talking about physical defects, what do you mean by physical defects over here?
Sir, can it be some dust particles, sir?
Dust particles, yes. And?
LER.
Lineage roughness. Okay, what would LER do, Deepank?
If it's a very low tech node, then it can impact the gates and basically make the device faster or slower.
तो electrical behavior हो गया.
Placement.
Placement
Means suppose if it's automated by a tool, suppose a metal layer has not been placed correctly or kind of stuff.
Oh, so if it is because of that, then it means that there will be zero yield because it's a design failure. You designed something wrong. What else? What do you call as defects? This is important also because this course is about testing also. So finally, we'll also test stuff. So it is important to deliberate on the definition of defects. What do you mean by physical defect over here? We just looked at the SRAM cell and how different layers simply pile up one over the other. Yes, Ranjit.
So defects could be dust particle which are being clogged.
Yeah, that Vaishnav also said. And
other than it can be the dielectric breakdown or some metals which can be metals which are being clogged.
Metals which are being?
Where the connectivity between the metals is being blocked.
Okay, so metals are not connected.
Yes, sir.
Okay, why would that be?
Sir, it can be that larger magnitude of current flows through this particular interconnect, and it can.
You're not talking about a fresh lot. You're talking about after aging. Okay, electromigration, stuff like that. Okay.
Yes, sir.
But what could be physical defects at the time of manufacturing? Think more in this direction that you were thinking about.
Sir, can it be because even we were saying one of the example in previous class. So the polys are not as good as we see in the layout. There might be some curvy nature which we simulate before fabrication. So
curvy nature. What do you mean by curvy nature?
Sir, I mean due to this
rounding. Okay.
Yeah.
So if you use curvy nature in an interview, they will be like, what is this? So rounding is the term.
Yes, sir.
There are some stuck-at faults that we study, but I don't know if they are applicable here.
Yeah, what is stuck-at fault? Why would it happen?
So
what is the defect that leads to a stuck-at fault?
So when there is a kind of shorting of a wire, or the wire gets stuck at the, if you want to toggle the 0 1, but it hits 1 only, like say it gets stuck at a particular logic, so then we call that as a stuck-at fault. And the fault, it could be due to the extra metal creeping in or the sand particles. I mean, there could be various faults that are modeled as stuck-at faults.
Okay.
So suppose this stuck-at fault can also be such that if the poly is shorted somehow to the VDD terminal, then the NMOS can continuously discharge to ground, and this can be a stuck-at 0 fault. Or else if the
very interesting. So can a poly be shorted to VDD over here in this layout? Is there a possibility there?
No, sir.
No? Why?
So poly, so VDD, we were providing it in like a metal 2, right? Because with the bit
Yeah.
line.
So this
And
this is metal 2. This is
yes,
the
sir.
metal 2 through which I'm providing my VDD.
Yes, sir.
So can the poly short?
So, but in between the poly and the metal 2, we would have the intra dielectric layer, right?
Yeah,
Kind of.
but is VDD going only in metal 2? Does your PMOS not get VDD at its source?
Mm, yes, sir. So, but it is getting through via connections, right? So,
Yeah, so it is getting it through via, then it is going to metal 1, then
so I mean, it would be connected through metal to metal 1 via, right?
okay,
And
then after
then
metal 1, what happens? How will it come to the drain or
so
the
it will
source?
through the tungsten contacts, right? That is throughout they would be coming to
Okay,
the
so
diffusion one.
if we look at poly, this is my gate, this is my device, this is my poly, and over here I made a contact, tungsten contact. Do you think there could be some shorting here?
Mm, yes, sir. They could be. I mean, but
Hmm? So in fact, in the memory cell, you will realize that the DRC between contact and poly is already violated. In a regular standard cell layout, you will maintain the DRC. In a memory cell layout, because they say manufacturability is, we know this is the pattern and this is the repeatability of the structure. So this DRC is already violated. The DRC is already violated means the probability of them just getting shorted is also higher. The dielectric is very thin over here. Are you able to see this? This is your poly, you etch that, but it is very close to your contact, where you have also violated the DRC. So this is the place where poly to VDD short can happen, and that would lead to stuck at 1 for one of the internal nodes. Are you able to see this? If this poly shorts to VDD, what happens? This metal one, everything, because it is connected to the poly, is now at VDD. So the node is stuck at 1. The other side will appear to be stuck at 0. Could a poly to ground short also happen like this? Is there a possibility of a poly to ground short also like this? Where we would get stuck at 0 and stuck at 1 in a different way? Look
So
at this.
maybe the poly which is near to the pull down.
So you could have stuck this one, for example,
yes,
this poly can, this poly and contact can get shorted. Okay, what else can happen? So this is shorting, stuck at 0, stuck at 1. What else can happen?
So can metals in different layers can somehow interact?
Metals in different layers, yeah, they will interact in
No,
a capacitive manner, coupling.
yeah, that's no in the although the DRC is being followed there, but still, is there a possibility like a tunneling kind of thing happen due to dielectric in the dielectric?
Intermetal, no.
Yeah, okay.
Intermetal, nahi. Intrametal, if you say yes, for example, if you see these two metal ones are very close to each other, right?
Yes,
There could be a short here. This metal one and this metal one very close to each other again can lead to a short. So whether this metal one and that metal one shorts, whether this contact and the poly shorts, what is the outcome? That this poly is held at VDD. है ना?
Sir,
Yes.
sir, in memory, we are much more concerned about the yield, right? So diluting DRCs, so how does that actually, I mean, and like I don't see any kind of, okay, we are saving the area, but we are actually I'm like compromising on the functionality, right? So why to dilute DRCs actually? I do understand that we are saving area, but
Area is diamond.
yes, yes, sir. But you see now you are explaining that this might happen. I mean, like we might get into a case that we are not even able. I mean, like we are not even coming out with a good functionality as such. So
See, let us say you reduced area by 25%. How much would your yield increase by? Do you know?
4 times.
No. You reduced area by 25%. So your area instead of A is now 0.75 A. So you increase your yield by 33%.
Okay.
Do you see the benefit of reducing area?
Yes, sir. I mean, I see both contradictory statements also, sir, at the first place, because now if you can see now we are violating DRS because we want to reduce area at the first place. So we are facing some issue over there, which might lead to some yield loss, right?
Yes.
So
let us say
again,
that marginal yield loss is 5%.
okay.
So what is the overall gain in yield?
So 33 minus 5, I mean 28.
You still gain 3%. Are you able to see this?
How is that 3%, sir?
33 minus 5 is 28. And
Okay.
earlier yield was
Yes, yes.
No,
sir.
no.
Yes, sir. I understood. I understood what you are saying. I mean, with more area, we are getting 25%. With less area, we are getting 33%. So 33 minus 28.
Okay. So no, actually it will be like 28% yield recovery. You don't need to subtract 25. 25% was the area was lesser. But you still have much more yield recovery, even in the presence of marginal yield loss. So you still would want to go to those DRC violations. But you want to recover yield from that also. What other things could happen? Chalo, ye batao. Abhi to humne, we just looked at shorting. What other things could happen? What other things could go wrong and can lead to faults? How many contacts and VRs do you have inside the memory cell? Did you do a count? Are you doing a count?
Sir, okay.
So how many contacts? Quick. Oh, huh?
10.
12.
12 contacts. How many via ones? How many via ones? So 12 contacts. How many via ones?
7.
7 कैसे होगा भाई?
नहीं 8 हो गया.
8. Okay. How many via twos?
4.
So just up till metal 2 or metal 3 level, you have 24 contacts and vias. All these contacts and vias are thin tunnels, trenches that you make, and then you fill them up.
Sir, this number will be even reduced, right? Because we are sharing them with the beside cell.
We'll come to the sharing part. We'll come to the sharing part. But to fail any one memory cell, you can fail any one of those 24 contacts or vias.
Yes, yes, sir. Yes.
Any one of those 24 fails, your cell would fail. So one cell, that many contacts and vias. And if you're talking about 1 megabit capacity, then 24 million contacts and vias. More capacity, many more. So do you realize the variations of contacts and vias are much more than the variations in your devices? There are only 6 devices, but 24 contacts and vias. So what happens? There can be failures. But and the interesting thing to note about it is that in a memory, many contacts and vias are shared. Some are shared across, for example, 4 cells. Some are shared across 2 cells, like this, rows. Some are shared across columns. So which contacts and vias do you think are shared across columns?
Bitline and bitline map.
Columns. This one. Which one would this be? That is shared along a row but across columns.
A word line.
Word line. Which one would this be? Vertically shared?
Bit line.
Bit line. What about this one, which is shared across 4?
Ground.
Ground. This could be bit line, this could be VDD, so on. So there are all these vias which are shared across the boundaries. So if the first one failed, suppose this one failed, how many cells would fail?
One, sir.
One cell would fail. If the other one fails, how many cells would fail now?
2, sir.
Now, so do you realize either that one fails or one of these fails, that we are losing 2 cells. If this one fails, how many cells would fail?
4.
So the same kind of defect, a via or a contact failure, can lead to 1 cell failure, or a double bit failure, or a quad bit failure. Are you able to see this? Same kind of defect, that so for example, the trench was not made well, and due to which the contact or the via failed. It can lead to single bit, double bit, or a quad bit failure. Are you able to see this? Hello?
Yes, sir. Yes, sir.
So in memories, you will realize, and when you will look at the silicon results, you will see that failures are typically single bit, double bit, or quad bit. Then in addition to that, you also have partial columns, or partial row failures, where a part of the row is failing or a part of the column is failing. But most of the failures in a memory are because of single bit or double bit or quad bit. So if you want to recover the yield of the bit cells, what do you need to do? You need to add 2 cells, 1 cell, 4 cells, or what do you do?
So I didn't get this part. So
So I say that, okay, because of the high density design that I have made, I can expect more failures, physical failures in my design. Is it clear till here?
Yes, sir.
So if there are more physical failures, I know I can anticipate those physical failures and I can plan to correct them. How do you correct a physical failure? You say, okay, I will discard the defective cell and I will pick up a new cell which is not failing. I will pick up another cell which is not failing. My question is, how would you pick up these new cells? Would you want to add just 1 or 2 cells somewhere? Or is there another way in which you will activate the new cells?
Sir, is that even possible to pick up the new cells actually? Because the thing which you are doing now is before fabrication, right?
This is after fabrication.
Oh, so
Fabrication has happened.
fabrication?
Fabrication has happened and you see there is a failure inside the memory array. There is a single bit failure. And you want to replace the single bit failure with another cell which you have already placed in a bank somewhere or in a location somewhere.
Is that even possible, sir?
Yes, you
Sir,
can put in some extra cells, no?
sir, maybe one approach could be that we will have the built-in self-test design implemented uh, for these cells, and then if that particular cell is set to fail, then the decoders will be such that we will be able to route this particular word line selection to the new bank or something like that.
Good.
Sir, there is one thing I have doubt. So, like after we had fabricated, then we would be doing the testing to figure out which cell is failing. And after we have figured out the which cell is failing, then we would be doing kind of selection. This
Yeah,
is what.
then we will do the replacement, because this
Okay.
cell is failing, I will replace this cell. If another cell was failing, I would replace that cell.
So that during testing, I would be able to locate the exact location of the failing bit cell, right?
Yeah, so now you understand why the scrambling information was very important.
Yes, sir.
Hmm? Okay, so what do we do now? Ranjit said, okay, let us replace the entire row. So if you want to replace the entire row, basically the decoder will select a different word line. Then what we need to add? In the memory array, we need to add, before anything else, an extra row, which is called as a redundancy row. Redundancy because it was not required, but we added a redundant row, which we would use if there is a failure somewhere. But we did not add just one row. We realized that 2 cells could fail, or even 4 adjacent cells could fail. If I had 2 rows, I can correct all such kind of failures. So if I can replace 2 adjacent rows, then even vertical dual bit defects or quad bit defects, I can correct easily. Are you able to see this?
Sir, 2 rows per cell. Yes. I mean,
2 rows per array I will add, or 2 rows I could add per memory also. That depends. That is my choice.
So like based upon the qualification that I do, I'm suggesting that at max, let's say 4 bit cells can fail.
No.
And
We could say there is one defect that could happen in the memory, which can lead to at most 4 cells failing.
okay.
This is the
So I mean,
maximum that one defect can cause.
so and how am I able to say that only one defect will occur, not more than one defect can occur?
So see, if more than one defect happens on every die, let us say, if more than one defect happens on every die, it means your process is not in control.
Okay.
As a designer, you can take care of some process idiosyncrasies, but you cannot take over the entire process. You cannot compensate for the entire process simply going haywire, especially not as a memory designer, where you are definitely constrained by a lot of area. See, if I was designing PLLs or something like that, then what happens? I have just one PLL in the entire chip. For that one PLL, I can also add some trimming bits. I can make the device to be large. I can do so many things because it is coming only once. But if you're talking about a memory cell, there are millions of memory cells there. You do not want to, add all those things. So you cannot compensate for process. So a PLL will compensate for process. A PLL will compensate for process variation, and then it will say, I will always generate 1 gigahertz clock. Whether you give me a slow lot, or whether you give me a fast lot, I will always generate 1 gigahertz clock. That is what a PLL does now. A clock generator does that. Whatever the thing you give it, whatever lot, it will always generate the same clock, isn't it?
yes,
Hello.
sir. Yes,
So
sir.
that is done by the use of some process compensation. For a memory cell, you can't do all that. You can do that. So what we say is we will add. So suppose this one fails. What I will do is I will replace 2 rows, either the row just above it and this row, or the row just below it and this row, and I will activate the repair row. So when this fails, the repair row gets activated and the failing row is removed. Pair of failing rows are removed. So whenever the new address comes, what do I need to do? I need to compare that address with the failing address. And if there is a match, I will select the repair word lines. If there is no match, I will go and select whatever word line was to be selected. Are you able to see this? Any questions?
Sir, can you repeat how we zero in on the failing row?
Oh, that we will run a best run. We will do a best run. We will test it and we will know this one is failing.
Okay, got it.
The defect location we can always find out through a test run. Na? Now we are talking about repair. To complete the repair, what do you need to do? You need to replace this particular row decoder and row with the repair one. How do you do that? You simply compare the address with failing address. If address and failing address match, the repair row deck will be selected. If they do not match, the regular row decoders will be selected.
So after my fabrication is done and I've located this my failing bit cell, then this kind of failing address would be, I would get to know about this information, right?
Yes. So once you know the failing address, you will have to program it. How will you program it? There is something called as one-time programmable memory or like fuses. So you will blow away some fuses on your chip and say, okay, this is the failing address. Is this clear? Now, what is the loss with this kind of a setup? What timing would get degraded, if at all?
Sir, the access to the memory will be larger. It will be a high latency because comparison logic will also be present.
Access to the memory or selection of the word line?
Yeah, selection of the word.
So address setup will increase.
Yes.
Hmm?
Yeah.
When the clock comes, the word line would immediately get selected. But what you need to do, which word line to select, that decision making takes longer now. So address setup increases. There is no impact on word line to queue delay. Are you able to see this? So a row redundancy implementation would lead to increased setup, but almost no impact on access time. Now, even if you do not become a memory designer, even if you become a computer architect or a digital designer, this piece of information would be very helpful as to which kind of redundancy to apply in different cases. Okay. Now, you remember we also talked about partial row failures. Why would they happen? Why could partial row failures happen or row failures happen?
So due to word line being stuck, like programmed by mistake at one point.
Yeah, due to some similar fault, contact being malformed or via being malformed or some short between some metal and some poly or something in the row decoder region, and then the word line would be selected incorrectly or may not get selected at all. So those row failures, how do you correct them? Again, by using this row redundancy scheme, you can correct partial row failures also. What if there was some sense amplifier which was failing? See, row decoder is still digital logic. The probability of it failing is lesser. The probability of a sense amplifier offset requirement being high and therefore a sense amplifier failing is higher. So how would you recover that if a sense amplifier fails? What kind of redundancy would you prefer in that case?
So the
column
inverter, the So we can basically tune the inverter such that, or the replica cells, so that the delay get, the sense enable delay I can adjust.
So if you adjust the sense enable delay on silicon, Raghav, then what happens? The memory would increase its access time.
Yes.
Wherever memory outputs were supposed to be latched, you will not be able to latch them now. So it's as good as a failure. So what do? Dipang said something.
So column redundancy. I don't know if it's possible.
Yeah. So what you would want to then do is you would use bitslice or column redundancy. I would not say column. I would rather say bitslice or a set of columns which share a sense amplifier. So what happens when you do this? Let us say a particular cell is failing. So you add a bit slice or a set of columns. Let us say a particular cell is failing. Then what do? You do not replace anything. You simply disconnect that particular bit line from the IO. And instead, you connect the adjacent bit line here. And then the adjacent bit line. And then you ripple it to the last IO. And the repair IO gets connected to the last IO there. So what has happened? So let us say you were initially storing bit 0 here, bit 1 here, bit 26 here. Now you're not storing bit 26 here. No. See, in the row redundancy part, what did we do? In the row redundancy part, if this was row 95, when the 95 address comes, the contents of row 95 are stored here. In column redundancy part, we do not do that. If it is row 26, I do not store row 20. If it is bit 26, I do not store bit 26 in this extra column. No, I store bit 26 in the adjacent bit slice. Then 27, which was initially 28. So this was 27. This is 28. So I just ripple it across, and then instead of storing bit 64 here, I store bit 64 there, and over here I store bit 63. Are you able to see this?
Sir, after fabrication, how are you? Like moving these wires as you want. Like,
so who said I'm moving wires?
sir, you said we will be moving to right side, so the wires
So
also move.
does connection always require moving wires? Do you know something called a mux?
Yes.
So how can you use a mux over here?
Okay, we are moving the mux.
You're just changing the control signal of the mux.
Oh, yes, sir. Got it.
No physical movement of anything is allowed on silicon, is it?
Yes, sir. Yes, got it.
All that you can play is with electrical signals. So you control the input of the mux. And the mux would select, until here, it will select 0th input. And from here onwards, it will select first input. Can it be done?
We are programming the control signal of the mux here. Like we are changing the control signal of mux.
Yes.
Okay.
Hana?
Sir, in this case, the bit order has, we are telling that the bit order has not changed. But the thing is that suppose if we find out that a particular column is faulty and we do the bit slicing, then immediately we run a read cycle, then the bit orders from which we read will be changed, no, sir?
So if you know something was failing, you know that, and you did a repair, Ranjit, then
Yes,
you know that you have not written into this extra column yet, and whatever you are writing or reading now is junk, is it not?
yes, sir.
So you will not read that junk. You will write into the memory all over again and then test it.
So then suppose if I have 1024 words, then all 1024 words should be rewritten again.
Yes.
And then there will be loss of data, no, sir. How do we retrieve and
We are simply testing, Ranjit. We are just testing. Testing mein to failure pakda gaya na.
okay.
There is no real data that we're talking about. It's all test data.
Isn't this during the runtime, sir? Or is it just before
How can you do this during runtime? How can you do a repair operation during runtime? Can you say that, okay, I know the memory is failing and then on runtime I will correct it there?
This was what I thought, sir, because we'll have some testability feature for each cell on the memory, and then once it is detected, automatically we change the control signals.
Yeah, but that is done in the beginning at the power up itself or during test itself.
Okay. Yes, sir.
Okay, so before the memory is written into for the first time during a real application, this correction is already taken place.
Okay.
Hmm?
Yes, sir.
Okay. Good. Thanks for this question, because I could see that many others could also be confused. Okay. What else? Any other questions on this?
So when we are designing replica path, so it should be designed beyond this row, and the worst case cell would be in this, in this column. Then
Yes. So when you are designing the replica path, you have to consider the redundancy column also to be a part of the memory.
okay.
Hmm? You cannot ignore it. So in many cases, as we saw, the replica path could be designed like this, in the center. In the same manner, the redundant column could also be designed in the center.
Okay, so it's equidistant. And
Doesn't matter. You could have a replica path like this, but the redundant column could be here also. These are all design decisions. You are free to do them, take them. But yes, you are right in saying that you have to ensure that the redundant column also does not fail. That you have to ensure.
okay, sir.
Okay. So I do not want to start with the next topic, which is cache design, just yet. But we do have some time left. So if there are any questions, I would be happy to handle them related to the projects or anything else. Have you guys started to work on your projects already or not yet? The projects were assigned last week, no? Early last week. So have you guys started to work on the projects yet? बाप रे, उस दिन तो कैसे बाल खींच खींच के लड़ाइयां हो रही थी क्लासरूम पे, और अभी तक आपने काम नहीं शुरू करा। तो लड़ाइयां तो बिल्कुल फ्यूटाइल थी जब काम ही नहीं करना था तो।
So we're just confused regarding what circuit should be and signals. These are the things we are doing right now.
So what is the project that you have, Deepak?
So replica IO. That's the
Replica
only
IO.
thing written there.
Okay, very interesting. So what all do you think would be there in the replica IO?
So our primary objective should be to generate reset and sense enable, as far as I can guess, and the input we would receive would be clock and the read clock and the work clock, and and I suppose we have to take care of. I don't know if the bit cell part uh, should be how, who will handle or how will we handle it. So we are still thinking about that.
So do you realize that in the
And
replica IO, you also need to have an input from replica bit line?
yes, sir. Yes, sir. We need a right driver. That's what I. Yeah, right driver भी चाहिए and.
There will be two different replica bit lines, one for read, one for write.
Yes, yes, sir.
So for
We
the
need
read
that
bit
detect
line,
also.
for the read replica bit line, what do you need?
For sorry, sir. Can just a second. For read replica bit line, I need an inverter only, I suppose.
You need a replica sense amplifier, which could be an inverter.
Yeah.
And do you need to pre-charge this bit line after the cycle is over?
Yes, sir. We need We would require to, yeah,
You
I
would
did not
require
think
some
about.
precharge
Yes,
also.
yes, sir.
Hmm? Okay. For the for the write replica word line, what all bit line, what all
Right.
do you need?
So write detect,
Hmm?
I need write detect and a write driver also
And you will need a
to
write
pull
driver
down,
also. So you will need
pull
write
down.
precharge also.
Uh, yes, sir. That right. I think write driver can have a mode sorry, it cannot. No, it would not be. Yeah. So the bchar should be common one, right? It should work
Whatever
in
it
both
is,
cases.
there are two different bit lines. One is
Yeah.
replica read bit line, one is replica write bit line. Both need to be precharged after the cycle is over, after the reset comes.
Yes, sir. Both should be. Yes.
है ना? So, okay, what else do you think should be there?
Uh, sir, there should be there are delay modes also. We can change
So
the speed of.
how would you do that? What do you mean by delay modes, and how would you include those delay modes in your circuit?
We can have a some set of NMOSes in parallel and activate or deactivate them based on the input vector given by the user.
Okay, so
To
that is one way. I would say there is a replica bit line, there is a replica sense amplifier. You read something. Now you want to trigger reset. Before triggering reset, you could just add chains of delays, and there
yes,
could
sir.
be a mux signal which you would help to select. Okay, which of the delays to be used.
Okay, yeah, that can be done via Mux also. But that
Hmm.
the other way was simpler. Yeah.
Whatever. So just check. Finally, it should
Mm.
be logically correct, and you should be able
Yes,
to simulate and demonstrate the functionality the way it is expected.
yes. Sir. And sir, doubt was what about the debug mode? What does that mean here?
So that was what Raghav was saying earlier. कि भाई sense amplifier Raghav था या Faisal था? Someone was saying that if the sense amplifier is failing, we will simply delay the SAE arrival. Who was saying? Raghav, you were saying?
I was thinking that.
Huh. So that is what is debug mode. That this is not a repair mechanism. I just want to find out if it is the sense amplifier that is failing, or if it is something else that is failing in a particular column. So I would
Okay.
activate the sense amplifier a little later. I do not know if the write operation failed or the read operation is failing. So I will bring the reset and the read operation a little later. So these are debug modes. They are to be used only during debug, during testing. They are not standard repair mechanisms, because if you use them as standard repair mechanisms, they will lead to different timings and can lead to failure elsewhere downstream.
Mm-hmm. Got it. Okay.
But they are useful for debug,
Okay.
for localization of faults, so that you can upgrade your design and do some learning for the next tape
Okay.
out.
So the control signal for this debug would be also given by the designer, right?
Yes,
Uh,
it can be an input pin.
yeah. Okay. Got it.
So you look at the data sheets and you will see that there is a range of input pins, and you need to
Mm-hmm.
design buffers for them. So all input pins, so whoever is designing the control regions, IO regions, or anything, all input pins should also have an antenna diode on them. What is an antenna diode?
To prevent the reverse current.
Why would this reverse current happen?
So for the source, you don't know what the source is, right? In an SOC, it should not reflect back the current and destroy the in circuit which provides the input.
So anyone who knows about antenna current, antenna diodes and antenna current? Okay. So let me see, is there a white slide somewhere? There won't be a white slide. Chalo, let me just clean this thing up and let me draw something here. So see, what happens is, on silicon, you would make different structures. Like you will make metal 3s, metal 2s, metal 1s, and so on. So let us say there is a huge metal 1. So there is a particular transistor, an inverter, whose gate is driven by a very long metal 1. And something like that. This metal 1 is then connected to a source or a drain from its another buffer, from far, far away. Huh? It's a long metal one, and over here there is a bridge, metal 2 bridge. What do you mean by metal 2 bridge? What would you mean by metal 2 bridge? So let us say there are two metal ones, and I just had a metal 2 because there was something else running in between, some other metal one running in between. I just had to use a bridge. So this is called as a bridge. Are you able to see this? So let us say this is metal 1, this is another metal 1, and this is VR1, and this is metal 2 bridge. Are you able to see this? Friends, please give me feedback. I'm on the other screen.
Yes, sir.
Okay. So let us say there is a bridge close to the driver, but there is this very long metal one which is fabricated and which is directly going to the gate terminal. Now, when you are doing the etching, so how do you remember the etching process? How do you design metal one? You would first fill the entire die, entire wafer, you will fill it up with copper. And then wherever you wanted to etch it out, you will put a mask and you will etch out the remaining metal from there. The remaining metal would be etched out, and there a metal wire would remain. You remember this?
Yes, sir.
The manufacturing process part. So when we do this, etching out, and when we do this high, a lot of ion implantation or whatever to remove this material, what also happens is in the manufacturing process, there could be a charge that could get induced onto these wires. Any wire, there could be a charge that can get induced. The longer the wire, the more amount of charge it can be induced onto it. Okay, so now we are saying there is this very long metal one wire, and charge can get induced onto it. Now this charge would remain there for a long period of time. Now you manufactured metal 1, now you will take your wafer to another part of the fab and you will now manufacture metal 2, and this manufacturing from metal 1 to metal 2 could happen 2 days down the line. So for that 2 days period, this charge is continuously applied onto the gate of this inverter. The gate dielectric can degrade and can fail. So this charge injection is called as antenna charge, and the failure is called antenna failure. Your metal has acted like an antenna and has collected charge from the ion beams that were striking it. Okay, and that leads to gate dielectric breakdown. That is antenna failure. Now, if you are designing, if everything is being designed inside the memory, the antenna failure DRC would appear and you would correct it. But when there are inputs to the memory, so on all inputs, you will have some input buffers. We do not know how far away their metal one is coming from. So at all inputs, we are expected to apply diodes. As soon as the voltage of this particular metal one rises above even 0.7 volts, not 0.7, these are, you will put these diodes so that as soon as the voltage rises above a desired level, they would sink extra current to ground. So all inputs have to have these antenna diodes put on them. Is that okay? You can read much more about antenna failures and antenna diodes online also. But in your designs, you have to design these antenna diodes there. Okay. So anything else? Yeah, yes, Vaishnav.
Sir, I am doing a project on 2-reader ATS RAM array, sir. IO circuit.
Okay.
So, sir, I am.
Sir, sorry to interrupt, but I needed to ask one more question regarding replica IO part. doing the same project. So we also have to build the self-timing circuitry over there. So I
What do you
mean,
mean by
how,
self-timing circuitry, Anushka?
sir, it was, I mean, mentioned over there that we have to, other than delay mode and debug mode, we had to write the self-timing, make the self-timing part also. But from what I understand, it is like more about the replica bit line and word line, because those parts, like uh, they make the reset signal go up, and then like that's how the self-timing happens. So how is it relevant on the replica IO part?
So you have to ensure that if there is a pre-charge, so you have to ensure all the circuits required for the self-timing path are there within your replica path, replica IO. As you're talking about replica pre-charge, replica write driver, replica sense amplifier, all that is also a part of self-timing circuit, no?
Yes, sir.
So that you have to make replica cells and replica bit line and replica word line. Someone else will make, but you have to make all this.
Okay, sir.
Okay.
Thank you, sir.
Yeah. All the best. Yes, Vaishnav, you had a question, no?
Yes, sir. So, sir, in this, it's mentioned that we are supposed to design pre-charge, write driver, and multiplexer circuit. So, sir, could you give a brief idea about I'm like how to fit that? I'm unable to imagine that diagram, sir. Exactly. I mean, schematic diagram of all these three together, sir. Pre-charge, write driver, and multiplexer together.
So there are three different blocks you will make, three cells you will make, and you will abut them. Why do you need them to be in one schematic? You would have a schematic for the pre-charge, which may have something like this.
Yes.
These are VDD, these are bit lines, and BL bar. And there could be an inverter here or something, PCH bar over here, something like that. So this could be a pre-charge circuit. And your write driver, as we saw, could be.
Yes,
so you make all these three circuits and you abut them?
Sir, my doubt was that because multiplexer is not a single thing that we do. I mean, so I'll make a circuit, and how do I multiply these circuits actually?
You repeat them. You abut them next to each other.
Okay, sir. Okay. Yes, sir.
No. So for example, for the pre-charge layout, what you should definitely try is that the bit line as it comes from the IO region should directly come to the source or drain. Okay. And that too not the cornermost one. Ideally, it should be like this, where, for example, if this is your active, you will make the equalizer over here, and you will make the VDD connections over here, and they will get shared with the adjacent bit line.
Yes, sir.
So the layout you have to make very carefully so that there is no extra space and loss of space because of the layout.
Okay, sir. Sir, can I ask a basic question, sir? I mean, I don't know, that's tool related dots, sir, actually. So, sir, if I abut this one after the other, so won't there be any kind of LVS error? I mean, I didn't try it out anytime, but I'm just.
You have to make the layout in such a way that there are no LVS errors.
No. I mean, my schematic is one only. I mean, I have only.
You have to repeat then the schematic also.
Okay, sir. Got it.
Otherwise, if you have stuff in the layout and not in the schematic, there is bound to be an LVS error.
Yes, sir. Got it. Yes.
Hello? Yeah. Anything else?
Sir. Sir, my time is designing the level shifting row decoder, sir.
Okay.
So, sir, in the level shifting row decoder, so at the first stage, we'll be having the dynamic NAND based structure.
Okay.
And the following cells would be a level shifters, which can be a basic inverter or it can be any other level shifter.
Can be skewed inverters, yes.
Yes. So, and they'll have so we'll be having two supplies, VDD1 and VDD2.
Yes.
Sir, then
I would say call them VDD array and VDD periphery. It will make it easier for you.
Okay, VDD array is the one which will be for the shifter.
For the word line.
for the word lines, and the periphery is the dynamic
address decoding. Yes, address decoding was applied.
Yeah. So sir, in this architecture, so it is said we have the choice of choosing 4 or the 5 input NAND gates, and it said it should also include the clock within those inputs. But as it is a dynamic NAND gate, sir, so the clock pins are separate, no, sir, as compared to the inputs.
They can be, you can merge one of the pre-decoded lines into a clock with the clock, and you can have that.
Sorry, sir, I didn't get it.
You can mix any of the pre-decoded lines, like suppose you have one pre-decoder which is 2 to 4 pre-decoder.
Yes, sir.
In that pre-decoder, you can mix the clock.
Okay.
In the control region itself.
Okay.
And then that will come there.
Okay, sir. Yeah. Yes, sir.
So you can reduce the gate stack at the post decoding stage by mixing clocks, by mixing other pre-decoded lines, all that.
Okay, sir.
Okay. Yes. Anything else? Okay, great guys. If there are no further questions, then we will meet on Thursday, and we will look at the we'll meet on Thursday, and we will look at cache hierarchy. Okay, L1 cache, L2 cache, the hit rate, miss rate, all those things we'll look at on Thursday. Okay, and I will also post a Google Classroom poll on whether we have our presentations on the day of the exam, that is 11th, or on say 15th or 16th. Okay.
Sir, there was a question in quiz, sir. I have a doubt in that.
Yes.
So following is the variation because of which cell ratio of 1 gives better sigma by delta than cell ratio greater than 1.
Sorry?
I'm reading the question, sir, actually. Following
Yeah,
is the
read
variation
slowly.
because of...
Read it
following
slowly.
Following is the variation because of which cell ratio of 1 gives better sigma by delta than cell ratio greater than 1. Shape variations, random variations, doping variations, and CMP proximity effect.
You tell me.
Sir, at the first place, I didn't understand the question only, sir.
Oh. So, okay. The question was about, see, there are cells which have cell ratio of 1. So PG and PD, the active region is straight. In another cell, the cell ratio is different than 1. So what happens? Over here, we saw that due to variations in the way this edge is formed, this device can be, the pass gate can be stronger and the pull down can be weaker. So that is why you remember we saw the example of Renesas instance where the yield of a high density cell was better than that of a high current cell.
Yes, sir. Yes.
Yeah, that is what it is being referred to, and it is the shape variations due to edges.
Yes, sir. Got it.
Okay. Yeah. So thank you guys. See you on Thursday then. And I have my office hours tomorrow also. We can, if you have any questions related to projects, you can join in the office hours also. I just wanted to check, did anyone of you get an opportunity to attend the VLSI design tutorial that I gave?
Sir, I am C.
Yeah.
Yes, sir.
So any feedback from that? Let me just stop the recording in the meantime.